Welcome to this video that does Unit 5 of Physics AQA Triple Science. This is for the beginner paper of Newton's laws. Question 1. When a force is applied to a spring, the spring extends by 0.12 meters. The spring has a spring constant of 25 Newton per meter. Calculate the force applied to the spring. This formula we are going to use, for this question we use F equals Kx, where F is the force, K is the spring constant, and X is the extension. So here, when a force is applied, the spring extends by 0.12, so X is 0.12 meters, and the spring constant K is 25 newtons per meter. Always do a check to make sure your units are correct, so distance should usually be in meters, and the spring constant in newtons per meter, and then we just combine them together in the formula. So 0.12 times 25 on the calculator will give you 3.0 newtons. So your answer to this question is 3.0. 2 marks here, one for the correct substitution, one for the correct result. Part B, figure 1 shows a toy glider. To launch the glider into the air, the rubber band and the glider are pulled back, and then the glider is released. Use the correct answers from the box to complete the sentence. When the glider is released, the something energy stored in the rubber band decreases and the glider gains something energy. So whenever you have a rubber band or a spring or something that stretches, so a stretching material, so let's say you have your rubber band here and then you stretch your rubber band out, you'll notice that you'll feel a resistive force. When you stretch it, it gains elastic potential energy. So if you have your rubber band and you pull it, it's got elastic potential energy. So the first one here, this will be elastic potential. And then when the glider is released, so when we release the glider here, what happens is that the elastic potential that's stored in the band converts to kinetic energy because it's going to movement. So when you flick a rubber band, as an example, the rubber band will go flying towards something. For example, if you flick it at your friend, then the rubber band will fly towards your friend, and that type of energy is kinetic energy because it's movement energy. 1 mark for each. Part II, figure 2 shows how the extension of the rubber band varies with the force applied to the rubber band. What can you conclude from figure 2 would happen to the extension of the rubber band if the force applied to the rubber band is increased to 6 newtons? So the rubber band does not break. So what happens here is, if we look at the graph, if the rubber band does not break, this means that this graph will continue, and if it goes off to 6, so the extension, so you can follow along here. If we draw a straight line here, because if we have force F equals Kx, as you extend the rubber band, it should be a straight line that continues at the same gradient. So you just get your ruler and you draw a straight line, and then at 6 you would then draw a straight line across to get a measurement. So you will get a increase to about 80. If you decided to continue the curve, that would also be correct. So if you said actually it continues and goes up like this, then you would also get the correct answer, because the correct answer is looking for anything above 75 millimeters in the extension. So what happens to the extension of the rubber band if you apply the force? The rubber band will increase extension, because as you apply more force, the rubber band, essentially when you apply more force to it, the rubber band increases. So let's say you have a rubber band and you hold it and you apply more and more force, the rubber band stretches more and more. And what you want to be careful here, there's 2 marks. You want to give, if you can, give a number on the graph. That's a key exam technique. So here you want to have an extension. So you could have an extension of 80 millimeters. Could have an extension of 110. In the mark scheme, we want anything above 75. So if you're above 75, then you get 2 marks. Part C, figure 3 shows vertical forces acting on the glider when it's flying. What is the name given to the force labelled B? B is acting downwards, and anything that acts directly downwards on an object is the object's weight due to gravity. So that's the force that is acting on the object, and that force will be B. Which one of the following describes the downward speed of the glider when force B is greater than force A? So if you have a force, so for example, if you push an object going in one direction and it has a little bit of drag in the opposite direction, then the bigger force will result in an increase in speed. So let's say this is A and this is B. So A is bigger than B, so therefore the speed will increase in the direction of A because it's got a bigger force than the opposite force. So in this case, A is bigger, so the downward speed will increase. Question 2. For the forces that act on this container ship are shown as A going up, B going to the left, C going down, and D going to the right. At the start, the ship is not moving because B and D are balanced. The ship begins to move forward, so when we have it going forward, so we can say that forward is going to be in this direction. So in this case, the forces that we're interested in are the horizontal forces because that's the direction we're going, and for it to move forward, B and D need to be unbalanced. So this one's B and D. When the ship is moving at a steady speed, so when it's acting at a steady speed, that means the forces are balanced. Okay, so when the forces are balanced, that means either the object is not moving, or if the object was travelling at a speed, it continues travelling at that speed. Basically, there's no acceleration. And in this case, this means that B and D must stay the same because they are balanced and they're travelling in the horizontal direction. When the ship stops at port, all the containers are taken off, and this changes the force. So in this one, this will change the force of C or A because this is the weight. So the weight is acting downwards, and that's equal to mass times gravity. When you take the containers off, the mass will reduce, and therefore the weight must also reduce because they're equal to each other. So if you reduce the weight, you reduce the mass, you reduce the weight. A is the opposing force that should be balanced, otherwise the ship will take off or sink to the bottom. So in this case, A will also reduce when the containers are taken off. So you could use either A or C in this answer. And 3 marks, 1 mark for each of the, so 1 mark for B and D, 1 mark for B and D, and 1 mark for C. The next one we got is question 3. A small object falls out of a balloon. Choose the words to complete the sentences. So the weight of an object is the force of. So when we have weight of an object and the weight acting downwards, W equals mg, weight equals mass times gravity. The force that weight is due because of gravity. When you drop something, first of all, so when you first drop something, what happens is that the weight is really big and the opposing force, if there is an opposing force, is very small. So this is the resistance R. What happens is that this is a much bigger force. We know that F equals ma, so if F is high, then the acceleration is also going to be high. So first of all, it will accelerate. When the faster it falls, the bigger the force of. So if you ever ride a bike or you ever skydived or anything, when you're falling or when you speed up, the resistance, you feel stronger air that's going towards you. So if you fall from the sky, you initially won't feel much air, but as you get faster and faster and faster, you'll feel a lot of air resistance. The same if you're riding a bike, or in an open-topped car. So as you drive along, If you drive slowly, you won't feel much air passing you, but as you drive faster and faster, you will feel the air, it will mess up your hair, etc. So that means that you have a bigger force of resistance, but there's not resistance in this option, but resistance here is the same as friction. So you can have air friction, so you could say air friction of the air is equal to air resistance. And then we also consider friction on the ground as well, and that's just known as a stereotypical friction. It means the same thing, essentially. It means a resistance. So what happens eventually is that the object will then fall at a steady speed. The reason why it falls at a steady speed is because the forces are balanced. So the weight goes down and the resistance is the same. If the resistance was bigger, then it would start to slow down, but what happens is they reach a balancing point where they both are the same, so it falls at a steady speed when both forces are equal. And this sequence you should know. Question 4, the figure 1 shows a spring before and during compression. The force F represents one of the two forces involved in compressing the spring. Draw another force, figure 1, to represent the force involved in compressing the spring. So if there is a force compressing the spring, the force is because of the weight, and we are going to draw a downwards force here. That is the force that's due to compression. So you should always draw your force directly from where it's coming from. Here you could also put it, I suppose, in the middle as well to show the centre of mass, but if you put it at the edge, it's fine, as long as you clearly show that the weight is causing the force, and this is the force that it wants in the question, so we'll call that force 1. Question 2, the student investigates 3 different springs to compare the spring constants. The results in the investigation are shown in figure 2. So in the first figure here, we've got height of spring in millimeters and force, and we can see the same in B and C. One thing that we notice, the way to think about this is there's 3 springs, and they all start from a height of 100. And what's happening here is that height is being reduced. So this one, for example, is, I don't know, maybe about 60. So now that one has been reduced to 60 millimeters, and this one's 100 millimeters. This one's not been reduced by much, maybe about 80, and this one's been reduced all the way to 50. So this one's had the most reduction when it's added the weight on. So these are 3 different springs, but they all start with the same height or length. So which of these springs have the smallest spring constant? So we have F equals Kx, and we want to find which one is the smallest spring constant. So we could say that F, we could rearrange this equation to get an equation due to F. So F over X is equal to K. And we can compare how the extension, because we don't know what the force is, but we know what, we do know what the force is, but we want to look at X. So if X is really big, then K must be really small, because there's an inverse relationship. It's a 1/over relationship here. So in this case, that is why the spring constant, we can use the formula to find which one's the spring constant is the smallest. So we could say here that the biggest extension, so the biggest X here is going to be this one, because it's the biggest change in it. This one's had a medium extension. This one's barely changed anything, so its extension is really small. And this one's had a huge change in extension. So it must be C as the smallest spring constant. How can we see this generally from the definition? Well, we know that F equals Kx. So that means that so K is the equivalent of force over extension. So this tells you how much, and you can tell this by newtons per meter. So if it has a small force, small k, that means that it only requires, so a small k means a small force needed to change the spring. So, give reason for your answer. We can see that it requires the smallest force or the most extension seen. So you can have two really ways. The biggest extension seen when a force applied. Remember, extension could also mean like basically the biggest change that we see. So yeah, that gives you your answer to this one. Figure 3 shows a child's toy. The toy hangs from a hook in the ceiling. The spring and the toy connected to each other. The toy oscillates up and down with a frequency of 1.25 hertz. So in this one, how many times each second will the toy oscillate up and down? So this comes from the definition of frequency. Frequency means per second, so it's the times per second. So this one would be, or you could say the oscillations. So this one directly you can read off the answer is going to be 1.25 because of the definition of what hertz is. Calculate the period of the oscillating toy, use the physics equation sheet. So for this one, the physics equation sheet you need is time period equals 1 over frequency. And from here, big T is equal to 1 over 1.25. Plugging that in gives us an answer of 0.8, which is our period. So this tells you the time period, the definition of time period is the time for one oscillation. So one oscillation will take 0.8 seconds. Here we've got 1.25 hertz, so we could just do 1 over that to find out what's the time for one oscillation. But this is a straightforward equation sheet. When the toy is stationary, the weight causes the length of the spring to increase from 0.05 meters to 0.25 meters, and the spring constant is 7 newtons per meter. Calculate the elastic potential. So first of all, we need to find a formula. That's the elastic potential energy, and again you would use your equation sheet. So the elastic potential energy is half kx squared, where k is the constant, or spring constant, and x is equal to the extension. So we've got the spring constant k is equal to 7, but we need to find x. We don't have x in this equation. So to find x, x is equal to the length after minus the length before, or the change in length. So that's equal to the length after it's changed, it's 0.25, and the length before is 0.05. So that's equal to 0.2 meters. Then we just plug it in, so the elastic potential energy is equal to a half times 7 times 0.2 squared, because it's x squared, which is equal to 0.14. So again, plug it into formula, nice easy one. If you know the formula and you know the definition for extension, then you should be fine. Don't remember, it's the change in these. So you must make sure you remember what extension is. It's not anything to do with a singular length. You have to find the change in the length. Question 5. A student suspended a spring from a lab strand and then hung a weight from the spring. Figure 1 shows the spring before and the weight is added. Which distance gives the extension of the spring? So this one, we're looking for the extension. The extension is just the change in the length of the spring. So in this case here, it starts, so J tells us from J to K, this gives us the original length of the spring. And J to L gives us the new length of the spring. But that's not what the extension means. The extension is just a change in the one. So we start from K, which is just at the top of the circle, to where the top of the circle is now. So this gives us the extension, so it's from K to L is your answer. Part B, the student uses the spring and a set of weights and a ruler to investigate how the extension spring depended on the weight hanging from the spring. Figure 2 shows the ruler is in a tilted position, not upright as it should be. How would leaving the ruler tilted affect the weight and extension data recorded by the student? Okay, so in this one here, we have, this is quite a tricky one. So we've got to think about what actually are we using to measure these ones. So here, the ruler is used to change the extension, but the first one we're looking at is the weight. Well, for the weight, we use a set of scales. So we use a scale because our formula is weight equals mass times gravity, but that's just used, we're weighing the mass essentially. So here we can weigh the mass, or find the weight of the scales, and therefore the weight that's recorded is going to be the same, even if the ruler is wonky. It doesn't affect the weight because you don't use that to measure the weight. However, the extension is going to be affected by this in this situation. So what happens is that when you measure the extension, initially, so you should have your ruler that goes like that. And if you do that ruler and you have, let's say your extension is here, okay, so this is going to be, so this is, hang on, let me draw a straight one. So this is your spring, and then this is your mass here. We'll start from there. Okay, so let's say that's your mass. Let's make it a bit, let's make it a bit smaller. Hang on. Okay, so let's say your mass is one of these squares, and you get your ruler and you measure it, okay, like this. You're going to get a measurement from here to here. But let's say I change my ruler, and now my ruler is wonky. So my ruler goes like this. So I get my, let's redraw it, sorry. So redraw this, and let's say that this is my one here. If you get a ruler and you measure it across like this, so you're trying to think, oh, what's the distance here? Then you're going to get a lower one because you're going to measure it separately. Oh, well, it's hard to show it visually on a board, but the idea here is that if you measure it across like this, you're going to get a smaller measurement of your extension because it's not going to be perfect, because your actual, if you measured it normally, your normal measurement would be somewhere here. When you bring your ruler round, your measured one would actually be here. So we can see that there's going to be a slight smaller increase. So the extension recorded by the student would be smaller than the actual extension of the spring. So if you change the ruler so it's wonky, then you're going to get a smaller extension than if you measured it properly. The student moves the ruler so that it's upright and not tilted. The student then completed the investigation and plotted the data taken in a graph. Use figure 3 to determine the additional force needed to increase the extension from 5 to 15 centimeters. Okay, so we have a 5 centimeters and we have 15 centimeters here. So the weight here is 2 and the weight at this point here is going to be 6. So the additional force that's needed to go from 2 to 6 is plus 4 newtons. So our answer here is just 4. What can you conclude from figure 3 about the limit of proportionality of the spring? So the limit of proportionality is the point where it stops being perfectly straight. And we can see that it stops being straight at around 7. So after this point it starts to bend round. So this here is the limit of proportionality. Okay, so what's so interesting about limit of proportionality? How would you answer this question? Well, you'd want to look at roughly when this occurs. So it roughly occurs around 6 point. If you zoom into this diagram, we could say that this is 6.4, 6.8, 7.2, 7.6, and 8. So it roughly occurs around 7 newtons. So this is really, an important one to remember, is that when it's talking about limit proportionality, you may have also talked about the extension, but you should also talk about the point where this occurs in terms of the added weight, because that's what really matters. How much weight can this material hold? That's what we're really interested in before it starts losing and becomes a plastic behaving object. So if you did both of them, you'd still get the answer correct, but make sure you talk about the weight that's being added on when you're answering these questions. A student repeated the investigation with 3 more strings, K, L and M. The results of these are given in figure 4. All 3 springs show the same relationship between the weight and extension. What is this relationship? So here we have extension and weight. We can see that it's a straight line. That means that the extension of the object is proportional to weight. Okay, as x increases, weight increases. So therefore they are directly proportional. If it's non-linearly, then you would see a line that's maybe a squared or something like that. If it's inversely proportional, then you would see the opposite direction. But directly proportional is a straight line, increasing straight line. And for part F, which statement A, B or C is used? So we're looking at spring M and we're comparing the spring constant to the other springs. So here we have F equals Kx. So here we can get K is equal to F over X. Now here we could look at the gradient, because the gradient here, if we think about a gradient of a straight line, M, it's change in Y over change in X. The Y part here is the extension, and the X part here is the force. So here we've got the opposite here, it's an inverse relationship. So what you want to do is flip these round. So if you change this, switch top and bottom, then you would also do 1 over M, because you're changing it over. So if you do 1 over X over F, that's equal to F over X. And if you do M, 1 over M, that gives you the gradient. So it's the same idea. So that's equal to each other. So therefore, if you have a small, so this is going to be the smallest gradient, so a small m. So therefore, we're going to have a, in this case, it's a 1 over a small m is equal to a big. So 1 over small m will give you a big value. What I should say is this is 1 over m, this is equal to f over x, and this is equal to k. So a 1 over small value gives you a big value, so therefore m has a big spring constant. Now this is really important question because it's quite easy to use this method and get it wrong, because all you're doing here is you confuse the gradients round. So you've got to remember that gradient is y over x, but the question might want you to do it the other way. So it's important that you remember that when you are doing your questions to check the axes. So again, so this one has the smallest gradient, but will result in the biggest k value because the axes are swapped over from what you need to use to find k. If this was force, so if this was the opposite way round, so the axes were force and extension, then m would have a really big gradient. So therefore you could see it directly. But in this case, because the axes are swapped over, then we have a smaller gradient. In this case, we can say m has a greater one. So the answer is C. The diagram shows an adult and a child pushing a loaded solid trolley. What is the total force on the trolley due to the adult and the child? So to find the total force, we add up all the forces that are acting in the direction. So if we look at the first force, that's acting to the right at 40, and the second force is also acting to the right at 10. So our result is 40 plus 10, which is equal to 50. So the answer is 50 newtons. Which one of the terms in the box means a total force? The same as a total force is the resultant force. Okay, so the resultant force you might have, for example, if you had 40 newtons and then the child stood at the other end and pushed it, so he stood here and pushed it backwards, then you would have a force 10. then the resultant force, or the total force, will be 40 minus 10, because 10 is going in the opposite direction. So that's 30 newtons, as an example of the difference between. So it's important, this shows the importance of direction of forces. If you've got a force going the opposite way, then you have to change the sign. The trolley is pushed at a constant speed for 80 meters. Calculate the work done to push the trolley for 80 meters. So in this one here, we use our formula booklet. Work done equals force times distance. The force, as we've said, the force from the previous question, although you will get an error carried forward, is equal to 50, and distance, newtons, and distance is equal to 80 meters. So on the calculator, you just put 50 times 80, which gives you a result of 4,000. Now the key thing here is the units. So for work done is the same as change in energy. So that means that your answer is in joules. And that answers your next question, BI. The work done, unit of work done, is in joules. Most of the work done to push a trolley is transformed into heat. Most waste energy, okay, or work goes to heat. So if you're ever stuck in terms of what something goes into and it's not obvious, like kinetic energy or something, most likely it will be heat and also wasted energy as well. Question 7. Which arrow shows the direction of the resulting force acting on the passenger train? So if it's going, the force is acting on the direction of travel. So in this case, the force is acting down the slope. The resultant force, okay, is acting down the slope because that's the direction that the object is traveling in. For part 3, the maximum gravitational force strength acting on the passengers. The reason why, by the way, the force is in this direction, you have a friction force. So if you look at the forces acting on it, you have the weight that goes down, but then you also have a resultant force, and you have the friction force that goes in this direction. If you combine the directions of these forces together, it gives the final resultant force, which is in this direction. It's in between R and W. For part of the ride, the maximum gravitational force acting on the passenger seems 3 times more than normal. Calculate the maximum gravitational force. So this one is nice. We've got G, which is equal to 10, but it tells us that here it's 3 times bigger, so therefore it's just 3G, or 3 times G, which is equal to 30. So a nice easy question here. It just tells you exactly what it is by reading the question. The maximum force is 3 times bigger than normal. Normal is 10, so therefore it must be 3 times 10. One of the passengers has a mass of 75 kilograms, so we'll calculate the maximum weight of this passenger. So again, G will equal 30, and the mass of the passenger is 75, and the weight is mg. So here we just plug it in, 75 times 30, which is equal to 2,250. Again, you can get an error carried forward from here, but hopefully it's a nice straightforward question. The diagram shows 2 forces acting on the object. What is the resultant force acting on the object? So here you've got one direction going 6 and the opposite direction is 2. So you need to subtract them because they're going in the opposite direction. So it's 6 minus 2, which equals 4, and it's going to the right. So 4 newtons to the right is the correct answer here. A base jumper jumps from very high buildings and mountains for sport. The base jumper shows the forces. The diagram shows the forces acting on a base jumper in flight. The base jumper is wearing a wingsuit. The base jumper accelerates forward when A, so A is acting in this direction, so if it accelerates forward in A, that means the force B has to be smaller than A for it to do it. So force A is bigger than force B. It's got to be bigger so that it can go forward. If it's the same, then it won't move forward at all, and if B is bigger, then it will move backwards. The base jumper falls with a constant speed c. When force C is something to D, well, if C and D are equal each other, then there's no overall force, so it falls at a constant speed. So this means it has to be equal to. If it accelerates downwards, then that means that D is bigger than C, so C is smaller than D. And if it accelerates upwards, so it slows down, for example, then C is bigger than D. But if they're smaller at constant speed, then they are equal to each other. To land safely, the base jumper opens a parachute. What effect does opening the parachute have on the base jumper? So in this situation, have on the speed. So the idea of a parachute is to slow it down. That's the general idea of having a parachute. So these we can, using your general knowledge, we can say that it slows down or reduces the speed. Probably a better answer. However, why is that? Well, the reason why is because in our previous one, if we had U, C and D, when the parachute opens, C is much bigger than D. So what happens then is that the object has a resultant force in that direction, and therefore it accelerates upwards. Now, by what does it mean by accelerate upwards? Well, originally the object is traveling, let's say at 80 meters per second. If it accelerates upwards, that means it decelerates downwards. So it slows down because it's already traveling in that direction. So therefore, your new speed might be 40 meters per second because the force upwards is bigger. So all you have to say for this question is that there is an increase in air resistance, or force C is bigger. And that will slow it down. And that will give you your 2 So either one of these two answers will get you the correct one. Question 9. Diagram shows a worker using a constant force of 60 newtons to push a crate across the floor. The crate moves at a constant speed in a straight line. Draw an arrow to show the direction of friction that is occurring. So here, friction is occurring to the left because it's acting in the opposite direction. Here now, the axiom accepts you to put it anywhere on the graph as long as you point it to the left. State the size of the friction. Well, as it's moving at a constant speed, the forces must be balanced. So we can say it's 60 newtons. The reason why is that it's travelling at a constant speed. Therefore, resultant force is 0, or the forces are balanced, or something like that. Calculate the work done by the worker to push the crate 28 meters. Show how you work out and give the unit. Okay, so first again is we're going to use the formula work done equals force times distance from your equation sheet. The force is equal to 60 and the distance is equal to 28 meters. So here we plug it in, 60 times 28, which is equal to 1,680. Work done is the same as change in energy, so therefore our answer is in joules. A powerlifter lifts a 180 kilogram bar from the floor to above his head, and we can see it travels a distance of 2.1. Use the equation in the box to calculate the weight of the bar. So here the mass of the bar in the question is 180, and G, gravitational field strength, is 10. So the weight is mg, which is 180 times 10, which is 1,800. The powerlifter uses a constant force to lift the bar a distance of 2.1 meters. Use the equation to calculate the work done by the powerlifter. So here its force in this question is 1,800 and distance is equal to 2.1. So 1,800, which is the force, times the distance, which is 2.1, is equal to 3,780. And then the correct unit, because it's work done, this is change in energy, so it's joule as the correct answer. At the end of the powerlifter holds the bar stationary for 2 seconds. How much work does the powerlifter do on the bar for these 2 seconds? So if the bar is stationary, that means that the work, remember, work equals force times distance. If the bar is stationary, that means that the distance is equal to 0, so the powerlifter does 0 work around your answer. And the reason why is because work is only done on the bar when the bar moves. Or something to that effect, something talk about how the distance is 0 and it's stationary. Question 11. On 14th October, a skydiver set a world record for the highest free fall. After falling from the aircraft, he reached a maximum steady velocity of 372 meters per second after 632 seconds. The maximum steady velocity is called the terminal velocity. So this is just a definition, which is the maximum velocity you reach is a terminal one. You can't go any faster than that. The skydiver wore a chest pack containing monitoring and tracking equipment. The weight of the chest pack was 54 newtons. Calculate the mass of the chest pack. So the weight is 54 newtons, G equals 10, and W equals mg. So here we want to find the mass. So we rearrange this equation. So we divide both sides by G. So weight over gravity is equal to mass. So therefore it's 54 divided by 10, which is 5.4. So the mass is 5.4 kilograms. During the fall, the skydiver's acceleration was not uniform. Immediately after leaving the aircraft, the skydiver's acceleration was 10 meters per second. Without any calculation, estimate its acceleration a few seconds after leaving the aircraft. So when he jumps from the aircraft initially, here he doesn't have any air resistance because he's only just jumped out. But a few seconds afterwards, he will have weight, but he'll have a little bit of air resistance that goes against it. So if he has some air resistance against him, that means that his acceleration downward is going to be reduced because he still had the same weight going down, but now he has an opposing force. So his overall force is left. Remember, F is equal to ma, so if the F total is reduced, because now you've got an opposing force, so here, if we say, let's say here that W is equal to 100, now if you have the air, let's say the air is, at this point, is 5 newtons, so it's going to be 100 minus 5, which is 95. And now we can see that the force is reduced, the mass is the same, so m is the same, and acceleration must also reduce if the force is reduced. So you could just do any estimate here, reasonable estimation, you could say 8, but anywhere between 0 and 10. And the reason why, explanation-wise, is that now you have some air resistance acting upwards against the weight. Therefore, this reduces the overall force, or the resultant force. Therefore, as F reduces, A will reduce, as mass is the same. That's a bit overkill really. The key things here is that you mentioned something that's acting against it, so air resistance or drag or an upward force, and then you say it reduces the resultant force. That will be enough to give you all 3 marks. And make sure you also put units here. Without any calculation, estimated acceleration 632 seconds after leaving the aircraft. So here it's got a time, but it's quite a long time. So here what we want to do is eventually the skydiver will reach terminal velocity, and that's where the forces are balanced. So if the forces are balanced, so F total equals 0, because that's when the balanced force. So balanced force means that the total force acting on it is 0 because they cancel each other out, therefore A is equal to 0. So estimate of 0 meters per second. And this is because we have the resistance equals the weight as we reached terminal velocity. Therefore, the resultant force is equal to 0 meters per second. And that's it. Oh, sorry, no, my mistake. So the resultant force is not 0 meters per second, it would be 0 newtons. And that brings the end of these questions. And if you have any further questions, please do let me know.